All right, good morning, everybody. So before we get into today's lecture material, I want to do a couple of things. One, I want to give a brief review over some addition chemistry before we get into the stuff that we're going to talk about today. And then I want to do a demo on the oxymercuration, demercuration. So I'll show you some, what I think is kind of some cool chemistry with it. So we know we can add things across pi bonds, especially carbon-carbon double bonds. We'll eventually get into carbon-carbon triple bonds. So what can we add? What do we know that we can add so far? What have we covered? We can add H2SO4 across the double bond? We can add water across the double bond, right? Yeah, so we can add water across the double bond, and we can use catalytic amount of H2SO4, a small amount of H2SO4. And what is that going to give me? We're going to get an alcohol. And what kind of alcohol? In this case, a tertiary, but it's a Markovnikov alcohol, right? So on my roadmap, I would put, in parentheses, I would write Markovnikov, and I would probably also annotate this as C+, indicating that there is a carbocation and there is the possibility of rearrangements. What else can we add across the carbon-carbon double bond? We can add halogens. Which halogens? As X2 or HX? We haven't talked about HX. Let's talk about HX, right? So we can add HX as long as X is what? Yep. So no F, right? No fluorine. What about astatine? Well, it turns out that there's only like 50 atoms of astatine in the whole world, so nobody knows, right? Because it's synthetic. It's not naturally occurring. So those are the ones that we can add. And what kind of product am I going to get? What's the functional group transformation? I'm going from an alkene to a what? To an alkyl halide, right? And I'm going to end up with a tertiary, right? And so this, again, is a Markovnikov addition, and it goes through a carbocation, so I have to be concerned about rearrangements. What else can I add? What else have we talked about adding across a carbon-carbon double bond? Well, we've talked about adding water across the double bond, again, using the oxymercuration sequence, right? And we'll do a demo here in a minute, but that would also give me a tertiary alcohol, a Markovnikov alcohol. But notice I'm not going to put C+ there. So there's no rearrangements, and that's why we need the oxymercuration demercuration sequence. What else can we do? We can do X2. As long as X, again, is chlorine, bromine, for the most part. Iodine, it turns out, is reversible. We'll talk a little bit about that. Technically, yes, but not practically. And so we can end up with adding X's across the carbon-carbon double bond. And it turns out, we'll talk today, but it ends up in anti-addition. So these aren't on the same face, so I'll just give it a little bit of stereochemistry there. So the two X's are trans to one another, if you will, right? One of the things that's in the reading that we haven't explicitly talked about yet is hydrogen. We can add hydrogen across a carbon-carbon double bond and get an alkane. Okay, so we can add H2 across the carbon-carbon double bond, but if you take a carbon-carbon double bond and put hydrogen in with it, the reactions takes millions of years for it to occur. We need a catalyst. What were some of the catalysts in your reading? Palladium, platinum, or nickel are good catalysts for this. Okay, so we can add hydrogen across a carbon-carbon double bond if we use either palladium, platinum, or nickel. Not all together, but either palladium, platinum, or nickel in the presence of hydrogen gas can do this addition quite easily. This reaction actually turns out to be very important for many of you. If you use solidified vegetable oils, partially hydrogenated vegetable oil, you've probably heard that term. That's what they're doing. They're taking vegetable oil, which has a lot of carbon-carbon double bonds. They're subjecting it to hydrogen in the presence, I think, of nickel. That's what they use in industry, and can convert an oil into a grease, basically. So it has a lot of value. The other thing that we talked about was X2 in the presence of water. And we'll talk a little bit more about that today, but we can form halohydrins. And we'll talk about the stereochemistry of that today as well. So, and there's going to be more as we add to this. But these are kind of some of the things that we've talked about already. All of these are electrophilic additions in some form or fashion, okay? And so today we're going to do a demonstration where we take 1 octene. 1, 2, 3, 4, 5, 6, 7, 8. That's good. And we're going to do oxymercuration, demercuration, which is going to be a 2-step sequence. What do I need for the oxymercuration step? What reagents? I need mercury acetate, I need water, and I need THF, or some solvent that's going to make everything soluble. Mercury acetate is somewhat soluble in water. Is 1 octene soluble in water? No. So, but I'm going to have something that gets everything mixed up. THF will serve that purpose. What is THF? Tetrahydrofuran. It's an ether. It's cyclic, and it's polar, and so it will be miscible with water. And then we do the demercuration step, which gives us what? Sodium borohydride is what we need, but we actually use this under basic water because sodium borohydride will react with just water at neutral pH or acidic pH, so you have to basify it. The hydroxide is not there to participate in the reaction. It's just to stabilize the sodium hydroxide. And in doing this, we should end up with 1, 2, 3, 4, 5, 6, 7, 8. Yeah, that's good. All right, so 2-octanol, right? We should end up with 2-octanol in the process. So let's look at that demonstration. So I'm going to put on some gloves. I'm dealing with mercury. Mercury gets a bad rap, right? Not a good thing to be working with most of the time. It's an environmental pollutant, but it's also a very useful element. So it is what it is. Use this as my table. And what I've got here is a little dish of water, just in case things start to get a little hot. I can kind of cool things down. In this flask, I've got some water, about 20 milliliters of water and some mercury acetate. It's not all solubilized. It's kind of precipitated out a little bit overnight, but that's okay. It'll be fine. What color would you call that? Kind of an orange color, right? And here I've got an equal volume of tetrahydrofuran. I'm going to pop that open. Now, what happens to mercury acetate when we place it into water? Remember, it forms an equilibrium, right, with mercury monoacetate, mercury cation, right? So I'm going to add the THF. The color change any? It kind of looks like orange juice. Yeah, that's a good analysis. Got a little yellow, a little more golden eagle gold, right? So we have a color change there. And now I've got my 1 octene. I got about 2 grams of 1 octene. And let's see what happens when we add the 1 octene. Try to get it all in there. We're going to stir this around for a while until the reaction occurs. So why am I in here demonstrating this to you all instead of having you go to the lab and do it? Yeah, working with all this mercury is a problem. Is it changing? Anything changing? Yeah, things are becoming colorless, right? And the stuff that's at the bottom, it'll eventually react if I sit here and stir it long enough. So what's happening right now? I am, so what am I getting? Oh, look at that. Nice and colorless. Nice and clear. What have I just made? You're on the right track, Anna. Okay. So I'm going to have an alcohol here, and I've got this carbon now is bound to mercury, right? This is called an organometallic species. I've just generated an organometallic species. An organometallic species is what? Any species where I have a carbon-metal bond. Okay, and they're kind of a special class of molecules. It's actually what I got my PhD in, working with things that had carbon-metal bonds. It turned out to be very useful in organic synthesis. But I think you will agree something definitely has happened, right? It's clear that we have, it's clear that we actually have had something occur. Well, I've still got a little bit of that mercury acetate at the bottom that hasn't quite reacted because it's on the bottom, and I don't think I'm going to wait forever. But if you look at that, does it look like there's a single, looks like everything's homogeneous, right, other than that particulate that hasn't reacted, right? Everything's homogeneous, and that's because THF is around. Right, so THF helps bring everything together. So it's not hot, so that's good. We'll probably see if I can't get the rest of that mercury to react. All right. Now what's the next step in the demercuration? What am I going to add? I'm going to add sodium borohydride. And what is sodium borohydride? What kind of reagent would you think it is? Hydride. It is hydrated, but it's not hydride. What do you think? What is hydride? What is chloride? What is ide? What is it? Tells us it's an anion, right? Sodium borohydride, NaBH4, sodium plus, BH4 minus. The borohydride has electrons, and electrons make good oxidants or good reductants. If something has a lot of electrons, does it typically reduce something or oxidize something? It'll reduce something, right? Because reduction is a gain of electrons. So if something has a lot of electrons, it's going to likely give them up to something else. And I think most of the mercury's gone now, so we're pretty good here. So now what I'm going to do is I've got about 15 milliliters of a sodium borohydride solution. And I'm going to add just a little bit of it. Ooh, look at that. What happened? A color change? What's it look like? I was going to say, what kind of chalk do you use? Okay, I get you. What do you think that stuff is? It's the mercury. And it's actually, if you look here, you can actually see little tiny spheres of mercury falling out of solution, kind of like rain. I always call this my mercury rain reaction. So I'm going to add a little bit more because I need to add all of it to get everything to go. But I'm trying to keep it from getting too hot on me. Is that what you all think that mercury looks like? What do you all think of what mercury should look like? Shiny silver, right? So why is this black? Anybody want to take a guess? Why is it black? Shiny silver ain't black, right? Any ideas? So what's happening? We are reducing off the mercury. Mercury's falling out of solution. And if you look, you can actually start to see it glob up and form what looks more like the mercury that you all are familiar with, the nice silvery shiny stuff, right? The stuff that is suspended in solution is little tiny like nano droplets of mercury, and that's why it kind of looks like rain. And until they start to come together enough, they never really form the shiny metallic. Look, but you can see it now. It's clearly, definitely mercury. And if you look carefully, what does it look like we have now? Looks like we have a layer on top. And that layer on top is forming because this has actually gotten warm, and THF doesn't have a very high boiling point. So I'm actually getting kind of high right now, smelling the THF, okay? And so the THF has been slowly boiling out. And as that THF has slowly been boiling out, right, it's not there to help solubilize everything. And so Do you suspect that this alcohol will be soluble or insoluble in water? It's soluble. It doesn't satisfy our 5-carbon rule, does it? And so now you can really see that we have metallic mercury in there, right? And so I'm going to have to go to the lab, take that metallic mercury out and store it forever because we can't just pour it down the drain, right, and dispose of it properly. But we have just done the oxymercuration demercuration sequence in just a few minutes. So I'm going to go ahead and put this over here, let it cool down a little bit. Now, let me just ask a question. Let me foreshadow a little bit to Chapter 9. Which, since you all have read ahead, you know that that's NMR, right? No, I'm being facetious. But how do we know that we got that alcohol? Can I go and do an IR and tell that I've got 2 octanol instead of 1 octanol? Probably couldn't tell much, right? Because OH gives a stretch about wherever OH gives it, right? Doesn't really depend on the position in the molecule too much. But NMR will allow us to determine it. And so I'm going to actually work this reaction up, and then when we get to the NMR chapter, we'll look at that NMR and we'll interpret it to prove whether or not I told you a lie. I didn't, but we'll prove it that I told you the truth, okay? That in fact, this gives the Markovnikov alcohol. Okay, so look for that. Now, we've also talked about another way of making alcohols where we can make the anti-Markovnikov alcohol. Let's just kind of to complete things here today. What reagents was, or what sequence was that? The hydroboration oxidation sequence. And you know the reagents for those. So, again, this roadmap stuff is very important for you all to be utilizing at this point, okay? Any questions about that before we move on? All right. All right. So, we're really close to Halloween, obviously. One of my favorite holidays. And so today we're going to continue on in Chapter 8. And we're going to talk about adding halogens across the carbon-carbon double bond, which we've already talked about a little bit, right? It's on our roadmap. And so we can take an alkene and we can take X2 when X is chlorine or bromine. Fluorine actually does work here, but it explodes. F2, when it comes into contact with most organic molecules, is an extremely exothermic reaction and it causes an explosion. So we ignore that one. Not particularly practical. Iodine will add to a carbon-carbon double bond, but it reverts. It goes back to iodine in the double bond. You all have done TLC, right, in lab? Did you all use an iodine chamber? Or did you just use UV vis? You used UV to detect? Well, it turns out that you can actually use iodine in what's called an iodine chamber, where it's just a glass jar where we put a few iodine crystals in. And on a TLC, if the material has carbon-carbon double bonds, the iodine will stick to that spot and make it kind of brownish. Okay? And it's adding iodine across the carbon-carbon double bond. And it gives you a visual indication. The cool thing is that when you take the TLC plate out and set it out on the bench for about 5 minutes, the spot goes away because the iodine is volatile and it reverts back to iodine plus the alkene. So that's a visual proof of that particular example. So if you look at typical alkenes, you can add halogens, either chlorine or bromine, across the carbon-carbon double bond, and you can get what we call vicinal dihalides. These are not gem dihalides, these are vicinal, meaning adjacent, right? And so you end up with 1,2-dichloroethane. Is it important that I say 1,2-dichloroethane? There's only 2 carbons, but it is important that I say 1,2-dichloroethane. Why? Because I could have 1,1 in theory. Not from this reaction, but in theory I can. So it is important to say 1,2-dichloroethane. Here I can end up with 1,2-dibromocyclohexane. This reaction works very, very well, very, very quickly. And you all actually come into contact with things that depend on this reaction. Again, back to my vegetable oil examples. Just like we can add hydrogen across the carbon-carbon double bond, we can also add halogen across a carbon-carbon double bond of vegetable oil. And it turns out that when you go and buy olive oil, you can buy a couple of different flavors, right? Extra virgin, virgin, and just plain old olive oil. What's the difference? You just know you go buy extra virgin because it's the most expensive, right? Why is it the most expensive? Well, partly that's true, but it's the purest stuff, right? It's got a lot of carbon-carbon double bonds. It hasn't undergone any level of oxidation that gives to an inferior product. And the way that they determine that is through titration, which you all have done in general chemistry, with a solution of halogen. And they measure how much halogen the oil will uptake. Does anybody know what the color of bromine is in solution? Think back to Gen Chem. You all used bromine water, I think, for a reaction at one point. Anybody know what the color was? It's kind of a reddish brown. Okay? So bromine is kind of a reddish brown solution. What do you think the color of the dihalide is? Huh? Nope. It is colorless. And so you can titrate the olive oil with bromine until the color just persists, and then you can determine the equivalence of the alkenes in a particular sample. And that's how they use that to determine whether or not a sample is extra virgin, virgin, or just regular old cheap olive oil. They can determine that through what they call the bromine number. Okay? Now the way that this reaction occurs, okay, it is an electrophilic addition in the first step. So halogen reacts with the carbon-carbon double bond, and we end up with what's called a halonium ion. If the halogen is bromine, we call it a bromonium ion. If it is chlorine, we call it a chloronium ion. Okay? But in general, if we're just talking about halogen, it's called a halonium ion. What's weird about this? What's strange about that? It's a triangle. It's a 3-membered ring. So what do we know about 3-membered rings? They have a lot of strain. They're unstable. But they're more stable than a true carbocation. So they form. How come we can do this here? What allows this to happen? What are the arrows telling you? What are these arrows saying? What are they telling us? How? What's it telling us? What's happening? Okay, we're going to have an octet for the carbons. That's true. What these 3 arrows are telling me is that the pi bond is reacting with the halogen, and one of the halides is leaving as a leaving group. That's kind of like an SN2 reaction, right? But notice I've got lone pairs on the halogen, right? And so that lone pair can react with the other carbon. So as that carbon is building up a positive charge, it is getting trapped, if you will, by the lone pair on the halogen. And so you never form a carbocation. We form a halonium ion. And since we don't form a carbocation, what don't we have to worry about? No rearrangements in this reaction. That's exactly right. But we do know that a 3-membered ring, especially a 3-membered ring with a positive charge on it, is strained and reactive. So this molecule now becomes an electrophile, and my X- is now a nucleophile. And so it will attack, the X- will attack one of the carbons. In this case, they're equivalent, so it doesn't matter which one. and this functions as a leaving group. It leaves from that carbon, but it's still bound to the other carbon. And because you have this three-membered ring, and we know that the nucleophile has to tack from the back side of this bond, that ensures that these two halogens have to be what with respect to one another? Anti. That's exactly right. They have to be trans to one another, if you will. Anytime you add halogen to a carbon-carbon double bond, it will be trans. 100% will be trans. It is a very well-behaved reaction. Okay? None of you could go into the lab and mess this up unless you dropped something and it broke before you ever got the stuff mixed. Because if once these two things mix, the reaction occurs. Okay? So, we go through halonium ion. And you need to remember, anytime halogen, X2, comes into contact with a carbon-carbon double bond, this intermediate is going to be formed. Okay? In the absence of another nucleophile, now it's going to be halide functioning as a nucleophile, and that's going to be a leaving group. You're going to end up with X2 across the double bond. But we also talked about being able to add OH and X across the double bond, right? If we had X2 and water. And sometimes water can function as the nucleophile, and so that's how you end up with the halohydrins, which we'll talk about here in just a moment. Okay? Now this has, because you go through this bridged intermediate, and because you end up getting anti-attack, that means that this reaction, okay, is going to be stereospecific. In other words, the stereochemistry of the starting material will dictate the stereochemistry of the product. So for example, if we start off with cis-2-butene and we do the chemistry, we end up with a pair of enantiomers. Cis-2-butene plus bromine gives me a pair of enantiomers. Why are these enantiomers? And non-superimposable. Does it have chiral centers? Absolutely. This is bound to a carbon, a bromine, a methyl group, and a hydrogen. 4 different things. This carbon is bound to a hydrogen, a methyl group, a carbon, and a bromine. 4 different things. Okay? And so we end up with a pair of enantiomers. However, if you use trans-2-butene and you did this exact same reaction, you would end up with the same product in terms of how things are connected, but not in how things are in space. And you would actually end up with a meso compound. Refresh my memory what a meso compound is. 50-50 would be a racemic mixture, but what's a meso compound? Well, it will be superimposable on its mirror image because meso compounds are achiral, but what is a meso compound itself? That's true. But what is a meso compound? You all are describing things that are a result of being meso, and that's good, but what does it mean to be meso? Ah, yes. It is a molecule that has chiral centers, but is overall achiral due to symmetry, mirror plane symmetry. And it turns out that there is a mirror plane that runs through this. And you may be looking at that going, no, there's not. There certainly is if you rotate around that carbon-carbon single bond. Okay? Trans gives rise to the meso compound in this case. Cis gives rise to the pair of enantiomers. I want you all for Wednesday to go home tonight, build your model kit, and convince yourself that this is true. Build the alkenes and imagine going through the halonium ion. You can build that 3-membered ring. You've got a flexible atom that you can build a 3-membered ring. Just pretend it's a halogen. And then look at another halide attacking. And if it started off as cis, the halonium ion would have the group cis, or if it's trans, they would have them trans. And convince yourself that you actually end up with a meso or a pair of enantiomers, okay, depending on whether they are cis or trans. Okay? You'll find that it's true. Okay? Now, we can do the same type of chemistry, again, chlorine or bromine, but instead of using an organic solvent that isn't a nucleophile, we can use water. Water turns out to be a pretty decent solvent for chlorine and bromine. You can get some bromine and chlorine in water. You can add it to an alkene and it will react. But you won't get X2 addition across the carbon-carbon double bond. You get X and OH. You get what's called a halohydrin. If it's chlorine, it's a chlorohydrin. If it's bromine, it's a bromohydrin. Okay? Help me through the mechanism. First part is exactly the same, right? So I take my alkene. Let's say we use Cl2. So what do I end up with? What's the intermediate? The triangle. Yeah, there we go. That is exactly the same as just adding chlorine across the carbon-carbon double bond. But what's different? Water functions as the nucleophile. We get the halohydrin. The addition is anti. Plus we get HCl formation. Okay, we got the chloride, and we have one extra hydrogen on the water, so that forms the HCl. I'm not showing the complete mechanism here, but most of it. Why does water function as the nucleophile when it's neutral, but chloride is negatively charged? Why isn't it functioning as the nucleophile here? If we think of this reaction kind of like an SN2 reaction, it's not exactly an SN2 reaction because the leaving group's not completely leaving, right? But the rate of the reaction should be dependent on the concentration of the chloronium ion and the concentration of the nucleophile. Will you all agree with that? And so if I increase the concentration of the nucleophile, what happens to the rate of the reaction? Does it increase or decrease? It increases. What's the concentration of pure water? This is a number you should know. No. That's its density. 1 gram per milliliter. Yeah. Have you ever thought that water has its own concentration? No. But water is dissolved in itself, is it not? So if I take a liter of water, it has a certain concentration. There's so many moles of water in that liter, right? So what's the concentration? It's 55.5 molar. Can I get anywhere close to that molarity in terms of chloride? Not even close. Not even close. So, which one is going to act as the nucleophile? The water, because it's huge excess, right? And we know that the rate of the reaction is proportional to the electrophile and the nucleophile concentration. So that reaction is going to go much faster than the reaction between chloride and chloronium ion. Okay? So the kinetics are starting to come into play here. We're starting to see all the stuff that we talked about before being important, right? And so we end up with these halohydrins, as we call them. So that's a new functional group that you all need to know. Okay, so we learned a bunch of functional groups at the beginning of the semester. This is a functional group. A halohydrin is a functional group that you can get, and they are useful for a variety of purposes. So just as we worked out, this is the mechanism, right? We go through that bridged halonium ion. In this case, well, what we did up here was the chloronium ion. And then here the water attacks, breaks that sigma bond. You end up with the oxygen-carbon bond and the carbon-halogen bond being anti to one another. You have a protonated alcohol. Water comes in and deprotonates that, and you end up with the formation of H3O+. And H3O plus Cl minus is really HCl, which is why I just wrote it there that way, right? And so you end up with this. So how could we monitor this reaction? Let's suppose Kaylin is coming into lab and she wants to monitor the rate of this reaction. How might she monitor the rate of this reaction? What technique could she use? You could use colors. What else could we use? You said something about acid, right? What do we know about acid? pH, right? So as the reaction starts, the pH should be about neutral. And as the reaction progresses, what's going to happen to the pH of the solution? It's going to become more acidic, right? And so she could measure that reaction that way, okay? And know when the reaction is over, okay? Now, it turns out that the combination of bromine and water is pretty effective to form bromohydrins. There are other reagents that are more practical. So, what all do you know about bromine, Br₂, other than the fact that it's kind of reddish brown? Has anybody ever worked with pure bromine before? If you're ever interested, come down to my lab. We've got several bottles of pure bromine, and we keep them taped up really well. And we keep them in a hood all by themselves because bromine's really corrosive. Okay, I mean, it oxidizes metals, and the cabinet that it's in looks like crap. I mean, it just, nothing you can do to keep it looking good. Okay? If you ever open up a bottle of pure bromine, this reddish brown gas just starts billowing out. And it's quite toxic. It'll kill you. I mean, it's kind of like the stuff they used in World War I for chemical warfare. Okay? They used chlorine gas. But it's the same kind of thing. It's not safe to inhale, okay? And so there are other reagents that we can use that are a lot more friendly, especially to students. So if I had you all come into the lab, you'd have to be working in a hood. It's a liquid. You'd have to somehow volumetrically pipette it, and you'd have to deal with all this noxious gas that and I don't want you to die, But it turns out there's another reagent called NBS, which stands for N-bromosuccinimide. And what NBS is, it's a white, colorless, crystalline material that gives off no gas. You don't have to wear a respirator. You don't have to use a hood. You just put on a pair of gloves. You get your spatula, and you go and you weigh this stuff out on a scale, on an electronic balance. And when this stuff is placed in water, it slowly decomposes into Br₂, which is kind of convenient for us, right? And so it turns out that if you take NBS and you place it in the presence of dimethyl sulfoxide and water, what's the purpose of the dimethyl sulfoxide? What is dimethyl sulfoxide? It is a solvent. What kind of solvent is it? It is aprotic, and it is also polar. It is a polar aprotic solvent. So it is soluble in water, and organic molecules are also soluble in it. So DMSO is actually used to help solubilize things into water, okay? Just like THF was in the previous reaction that we looked at, okay? But when I mix these things together, anytime you see NBS, DMSO, and water, you should immediately think that is nothing more than Br₂ and H₂O. That's how it behaves, okay? And so I can take my alkene, NBS, DMSO, and water, and I can get my bromohydrin, okay? It works just the same. Okay? And so if we look at some chemistry, so here we have cyclopentene, bromine and water. Notice we get the trans addition of bromine and OH. These are chiral centers. We end up with a pair of enantiomers. What ratio? 50-50. So this is also known as a racemic mixture. We're going to end up with a racemic mixture. Okay? Notice it doesn't really matter which carbon here gets the bromine or which carbon gets the OH, because there's symmetry, right? Now, what if we have an alkene that's not symmetrical? It matters. Okay? And so you will end up, if you take isobutylene and react it with bromine and water, you will get this product. Notice the bromine is on the least substituted carbon, and the OH is on the most substituted carbon. Whose rule is this? This is Markovnikov's rule. Bromine is nothing more than the electrophile. Water is the nucleophile. So we can form this in a Markovnikov fashion, just like we can form alcohols in a Markovnikov fashion. So explain to me why is it that the OH attacks the most substituted carbon and not the least substituted carbon? So why is it that water is attacking this carbon and not that one? It's attacking the most substituted carbon. Right? The OH is going to end up on this carbon. Not on this one. Where else have we seen a three-membered intermediate that undergoes this type of addition? Oxymercuration, demercuration, right? Is the explanation going to be any different? So why? That's right. I've kind of drawn it in a way that tricks you, right? It turns out that one bond is longer than the other, right? So we have something a little more like that, right? Meaning that this bond is stronger or weaker? It is weaker. So a nucleophile will go after the weakest bond, okay? And so it's a little counterintuitive because in SN2 chemistry, we always talked about preferring to attack the least substituted carbon, right? If you think about it, tertiary alkyl halides didn't do SN2 chemistry, but primary alkyl halides did, right? But there the bonds were about the same strength, and so it was all about sterics. Here, it's not about the steric environment, it's about the bond strength. And this bond is extremely weak. And so it will break a lot easier than the less substituted carbon bond will. Okay? So you can see it here. We go through the halonium ion. Water then acts as the nucleophile. You end up generating the protonated alcohol. That then gets deprotonated and you form H3O plus and Br minus, which is nothing more than HBr in water. And so the pH will increase as this reaction occurs. What's not fair in this particular mechanism, although you can't account for everything, is if you look at this, you would say, well, water is a neutral nucleophile, bromide is a negatively charged nucleophile, and we learned in a previous chapter that negatively charged nucleophiles are better. And so if you just looked at this, you would still predict that bromide should do the chemistry. What's not accounted for is the fact that there's a ton of water around this molecule. It's not just one water molecule. It's lots of water around that molecule, right? And so bromide in water also has a solvent shell of water around it, right? So that hinders its nucleophilicity, and you've got all this water around. So water's going to behave as the nucleophile. So all those things that we learned about in terms of naked ions and hydrogen bonding to an anion and all that kind of stuff, it's important here, and that's why we're seeing water behave as the nucleophile as opposed to the bromide, okay? It turns out that this is a pretty important set of reactions to make a variety of different pharmaceutically active molecules. This is an example of making estrone, which is a female sex hormone. Being able to make these types of things is very, very important, especially in things like contraception and other things. You've got to be able to make the hormones synthetically, and so Halohydrin formation is one good way to do it. Industry has chosen to take this carbon-carbon double bond, which is part of a kind of this hormone ring system, if you will, and so this is a carbon-carbon double bond. This is an aromatic ring, which doesn't behave like carbon-carbon double bonds. We'll learn about that in another chapter. And so they basically put this in water and bubble chlorine gas through it, and you end up generating this chlorohydrin. Now that chlorohydrin can react to give this three-membered ring. Does anybody know what this is called? What functional group is this? It's not a ketone yet. It will be a ketone here, but that's some other chemistry. What is this functional group? That three-membered ring. It is an ether, but what kind of ether? What do we call them when there's a three-membered ring? There's a special name for that. These are called epoxides. They are three-membered ethers. Ethers are typically not very reactive, but epoxides are. For those of you in polymer science, where have you heard the term epoxide before? Everywhere, right. Epoxy resins, right? These are useful for like glues and other things. They're useful for that. But they're also useful for making these types of molecules, okay? So you all have in your toolbox all the chemistry you need to show how this chlorohydrin becomes this epoxide. Take a minute, talk with your partner. How does that happen? Oh, okay. Well, that's fair enough. You left your toolbox at home? Never leave your toolbox at home. Who's got some ideas? What's going on? Okay. Oops. A partial? Okay.
And so that's going to pull the oxygen to it, and the chlorine will break off.
That's it. Acid, base. Base, acid, epoxide. Okay? It's nothing more than a series of Lewis acid, Lewis base steps. We're going to stop there for today. I will see you all on Wednesday. Have a good one.